Okay, so today we're going to be talking about enthalpy and entropy. Now, enthalpy is the energy or heat content of a substance. Um, let's use red. Okay, so we represent enthalpy by H. H is enthalpy. Now, we've been calculating the delta H, or the heat of reaction, the change in enthalpy from our potential energy diagrams. Now, this delta really means the change in something, or the difference between something. So this change is really the change of the potential energy of our products minus the potential energy of our reactants. And there's our heat of our change of enthalpy. Now, in nature, there's a tendency to change to a state of lower energy. So, going home after a long day of work, it's nice to sit on the couch and have less energy compared to being really productive and spending a lot of energy working out, even though that's what we should be doing. But it takes more work to do that. It's against our tendency to go to a state of lower energy. Now, that might be a bad analogy, but when we have reactions, when we have the products that have less potential energy, those are the reactions that are more favorable. So as we look at this graph right here, we have our reactants over here, and it has more energy than the potential energy of our products. So this is an exothermic reaction, and it's also a reaction which is more favorable. The products have less energy, they're more stable. And the other reason why it's more favorable is that these reactions require less activation energy than endothermic reactions. So as you can see, this activation energy, AE, remember our activation energy is the energy from our activated complex to the energy of our reactants. Now, this is a lot smaller than the activation that we'd have from an endothermic reaction, in which our potential energy from our reactants, there's a bigger increase to go all the way to the potential energy of our activated complex. So this activation energy is a lot bigger. Also, our products have a lot more energy, or a lot more energy than our reactants. So reactions that are exothermic are more favorable. So here's some examples. Practice which reactions are favorable reactions. So N2 to H2 goes to ammonia plus heat. Now this is showing that heat is on the right side of the graph. It's giving off heat. Remember, reactions that give off heat are exothermic. And since exothermic reactions are favorable, this one is a favorable reaction. Now, if this heat was on the other side, it would be saying that it would require a heat to for a reaction to occur, and that would be endothermic. That would not be favorable. This next one, we have N2O2 going to NO2. Now, we would look at our delta H over here, and it is a positive 33 kilojoules. Remember, our delta H is products minus reactants. If we have a positive delta H, that must mean that our products have a lot more energy than our reactants. And if our products have a lot more energy, it is not favorable. The next one is a potential energy diagram showing that our reactants down here have a lot less energy than our products up here. So this one is, again, not favorable. The next thing we're going to be talking about is entropy. Entropy is the disorder of a system. And nature has a tendency to change to a state of greater randomness or disorder. It's like if I had a deck of cards, a brand new deck of cards, they're usually ordered by suit, and they're also ordered from king through ace. King through ace, king through ace, that's a lot of order. And if I took that deck of cards and threw them on the ground, played 52 card pickup, there's a very small chance that when I pick up all those cards again off the floor, that they're going to be in the exact same order as when we started. They're going to get into a more disorder. There's going to be suits all mixed up and numbers mixed up, and um, that's nature's way to change to a state of greater randomness or disorder. Now, there's different things that can increase in entropy. Now, when we say we're increasing entropy, we're saying that we're increasing disorder. So, one thing that does increase disorder is an increase temperature. So, if we're increasing temperature, that's really saying that the particles are moving a lot faster. So if they're moving faster, it's basically creating a lot more chaos, a lot more random movement. If we have a beaker here and they're moving faster, all of a sudden they're going all over the place. But there's a lot more disorder compared to if they're going really slow and going beep, beep, beep. So as we increase temperature, there's going to be more disorder and randomness. Now, as we learned from a couple chapters ago, remember that solids have a lot less energy than liquids. Liquids have a lot less energy than gases. Now, this aqueous, this AQ, that's standing for aqueous, or substances are dissolved. And dissolved substances fall somewhere in between liquids and gases. Now, there's another thing that can increase entropy or increase the disorder, and that's if we have more particles. So it's kind of like if we have a room and I have several of my dirty clothes, my shirts and pants and stuff laying on the ground, and then if I end up throwing 18 more things on the ground, I'm going to increase the entropy. So as we increase the number of particles, we increase the disorder. So an example right here, we go from 2 particles over here to 3 particles over here. We're increasing the entropy. So in this example over here, let's just look at the states of matter. If we have a gas, and we're going to a liquid. Now again, gases have a lot more energy, and we're going to a product that has a lot less energy, which means we're going to a product that has they're moving a lot slower, which means that it's more ordered. If it's more ordered, it's a decrease in entropy. So the next one, we're going from a liquid to gases. Now gases move a lot faster, they have a lot more energy. So if they're moving a lot more faster, they're kind of going all over the place. They're going all over the place compared to a liquid that basically just chills back here, down at the bottom. We're increasing the randomness, so we're increasing our entropy. So this one is a favorable reaction. Now, reactions will occur spontaneously if the enthalpy is exothermic, or if the products have less energy, and entropy is increasing, or if we're getting more disorder. So both are the favored tendencies of nature. So if we have some reaction which is both exothermic and increases entropy, we're going to have a very favorable reaction, and it's going to occur in nature without any outside help. So this is what we're going to be learning tomorrow in class. So come to class prepared, and I will see you tomorrow.